Hello and welcome to our lecture on carbohydrate digestion. So looking specifically at the carbohydrate as it moves through the entire alimentary canal, from mouth to rectum and anus. We'll look on the left side, we'll look through starches, kind of an overview, and on the right side we'll look at fiber, kind of as an overview. So starting in the mouth, we see, again, salivary amylase. We've heard this term before. Amylase will begin to work on some small polysaccharides. We do also have the mechanical digestion in the mouth, which is the chewing and the tongue moving food around. So then from the mouth, we will swallow the carbohydrate molecule into the stomach through the esophagus. And here we don't have a ton of work on carbohydrates happening, particularly because it's too acidic of an environment. So then the carbohydrate would pass relatively unchanged from the mouth through the stomach into the small intestine, and here's where we really see the work of the pancreatic enzymes. So we see amylase, maltase, sucrase, and lactase. Again, amylase is basically working on those polysaccharides, breaking those down. Once polysaccharides have been broken down into disaccharides, this is where we have other specific enzymes working per the specific disaccharide. So again, maltase will work on anything that's glucose bound. Sucrase will work on anything that's fructose and glucose, or sucrose. And lactase will work on the galactose glucose and break that. And then from the small intestine would be absorbed into the bloodstream and either delivered to body tissue for immediate use or delivered to the liver as kind of that switchboard to figure out, all right, do we need to store this right now, or is some organ going to use this relatively immediately? And then we'll look at fiber on the other side. So again, we see the mechanical action in the mouth of chewing, tearing, breaking, starting to break the fibers apart. And then again, passing basically through the stomach unchanged. One thing though about fibers in the stomach is that it will just kind of slow things down because they're kind of these large complex molecules that can't really change too much in the stomach. So it just kind of naturally slows digestion. And then from there, the fiber would move into the small intestine. And again, not a ton of digestion happening here. But then we see in the large intestine, still most of this most of the fiber is going to pass through, but particularly soluble fiber will be in the large intestine. We'll see the action of bacterial digestion on those soluble fibers. But in addition to that, in the large intestine, we'll see that fibers, especially again those soluble, will start to absorb some water or kind of bind water a little bit, as well as binding some other cholesterol molecules and in some cases minerals too, and then eliminate them through stool production. So again, kind of the schematic overview. So starting with your starch, amylase would work on starch to start breaking it down into 2-unit disaccharides, maltose, sucrose, or lactose, and then specific enzymes to work on each one of those and break them down to the monosaccharides. And then it's the monosaccharides that get. So here's where we will see that monosaccharide absorption. And again, we looked at this quickly in the previous slide, but fructose will be absorbed via facilitated diffusion, and glucose and galactose will be absorbed via active transport. And then right here, they're being absorbed into the enterocytes, and then from the enterocytes requiring another carrier to move them into the blood supply. So on this slide, we're just looking at what kind of brief overview of what might happen with glucose. So typically, fructose and galactose, if we absorb them, they're going to go straight to the liver where they'll be converted to glucose. And then glucose, we can either send it out to, glucose could actually travel immediately from being absorbed from the enterocyte could go directly to various body sites where it might be needed. So maybe working muscles need it, maybe the heart, maybe the brain needs it. So glucose might move immediately to some other tissue site to be used for energy. If the body does not need glucose, say for example we've eaten too much and we've digested a bunch of food and we have this excess glucose, it's a really important nutrient to us, so we will hold on to it. And we'll do that typically in the liver. So in the liver, we may convert excess glucose to glycogen. Similarly, if we were really hungry or just done a lot of movement or exercise and the muscles are also depleted of their glycogen stores, then we will see muscles also storing glucose as glycogen. And just a little for your information at the bottom, the liver can usually store roughly 280 calories worth of glucose in the form of glycogen, and muscles can usually store somewhere just shy of 500 calories worth of glucose as glycogen. So you kind of get the sense most of us require a bit more than 800 calories per day to survive. So what we can store energetically as glycogen is not really enough to power the body for much more than a few hours. So this is pretty important, is this concept of blood glucose level. So the amount of glucose that's existing in our blood supply at any given time is a really important aspect of homeostasis, or maintaining kind of neutral equilibrium within the body. So we see actually two primary hormones, insulin and glucagon, kind of work together in sort of a negative feedback loop to keep blood glucose at a normal range, which is usually going to be somewhere around 80, but would depend on the person. And then cortisol, growth hormone, epinephrine, and norepinephrine do also play into this blood glucose regulation. So insulin, the job of insulin is let's say, the pancreas will produce insulin when blood sugar gets above the normal range. So usually that's when we've eaten something, we have sugar coming into the blood, thus raising blood glucose above that normal homeostatic level. So insulin's job is to tell various tissues throughout the body to take in glucose from the blood supply, thus bringing that blood glucose level back down to the homeostatic level. Glucagon is again has just the opposite job from insulin. So when blood sugar is below homeostatic level, like when we wake up in the morning, or if we haven't eaten for several hours, then the pancreas will secrete glucagon, and glucagon will go and act at particularly sites where we have glycogen storage, so liver and muscle, and we'll say, hey, break down your glycogen store to release the glucose into the blood to bring the blood glucose level back up to a homeostatic level. So these two words, glycogenolysis is breaking down glycogen, glycogen lysis, glycogen breakdown. Glucose, neogenesis. Gluconeogenesis is another thing that can happen throughout, particularly in the liver. So that's what hepatic is, liver. Gluconeogenesis is where we make glucose from non-carbohydrate substance or non-glucose substrate. So amino acids, we can take some amino acids and convert them to glucose. We can take fatty acids and convert them to glucose. So if we have an issue where blood glucose is low and we're not eating, glucagon, in addition to telling the liver and the muscles to break down glycogen and release glucose into the blood to bring up blood sugar levels again, glucagon will also act on the liver to tell the liver to start making glucose from amino acids and fatty acids, and thus release that glucose into the bloodstream to bring blood sugar or blood glucose levels back up to the homeostatic level. And then cortisol, epinephrine, and norepinephrine, these are all kind of our fight or flight or stress response hormones. So when we're sort of high cortisol or kind of high stress, and not necessarily a bad stress, but when we're sort of feeling that heightened sense, these three hormones will actually act on the liver and the heart to increase glycogenolysis and gluconeogenesis, particularly again in the liver, and thus increase blood sugar levels. So again, if we're stressed, the biological assumption is that we kind of need to do something. We either need to run, or we need to fight, or we need to, like, action needs to happen. And so sensing this heightened state of action, the body is saying, okay, let's get a little more blood sugar. Let's raise blood sugar levels a little bit so that we can get this energy substrate, glucose, to various, especially the muscles, to do this action, whatever action is going to need to happen. And then growth hormone similarly will raise blood sugar levels. But typically, well, in addition to glycogenolysis and gluconeogenesis, growth hormone will encourage lipolysis or lipid breakdown in adipose tissue. So increasing the free fatty acids available to convert to glucose to raise blood sugar that way. And then here's just a schematic of basically insulin and glucagon. So again, your normal glucose levels somewhere around 70 to 80, mid 80s if you're fasting, and then usually somewhere in the low to mid hundreds after a meal. But then within about 4 hours after meal, we'd see that blood glucose come back down to the sort of 80, 75 to 85 range. So you'll see kind of all the actions of insulin with the end goal of increasing, insulin coming about when blood glucose levels are too high, with the end goal of bringing blood glucose levels back down to a homeostatic level. And then again, kind of in a negative feedback loop, glucagon, if blood glucose levels get too low, glucagon has various actions, all with the end goal of raising blood glucose back to homeostatic level. And a couple schematics, again, just looking at blood glucose. So normally after a meal, we would see blood glucose levels rise. That's that red line. And then similarly following it, insulin levels would rise. As insulin rises, it's telling cells to uptake glucose, so you'll see blood glucose starts to go back down. And again, if we had another snack, blood glucose would come back up. And so then interestingly, showing here the dotted line versus the blue and red. But I need to look at this for just a second. So sucrose-rich foods, these would be anything with table sugar in it. You'll notice how the response with blood glucose rise and insulin release, it's kind of a spike. It's kind of much higher with sucrose-rich foods compared to starch or more complex carbohydrate foods. You'll see that spike is much lower. And then what you'll also see is after that sugar-rich meal, you'll see that blood glucose drops much more substantially. So we kind of like to keep things a little bit more even keel. The body likes to keep things a little bit more even keel. So this spiking really high and then dropping really low, ultimately, if this persists continually day after day, that could lead to something that we call insulin resistance, where the body cells stop responding so well to insulin. And just showing this again. So looking at the blood sugar response to sugar-rich foods and then the subsequent crash. The blood sugar response to processed foods, but not necessarily sugar. and then the response to whole foods. So again, kind of that staying within a healthy blood sugar range. And again, this would be on the low end. This would be like 70, 80 if you're fasting, and this would be like 140 or so a couple hours after the meal. And then just kind of showing it again one more time. So where we see the blood sugar spikes could be with excess sugar, but also with can be with too many calories, which also results in high blood sugar drops. And then also skipping meals can result in blood sugar drops. And so you'll notice that just kind of keeping it stable with healthy whole foods keeps the body in a more comfortable homeostatic level.